Pluto is a faraway and subtle, truly fascinating celestial body that was once a part of our planetary framework. However, recent claims by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight. They proposed that this distant world is on a potential impact course with Neptune. But how could this actually happen? What might be the consequences of such a significant event? Are we witnessing an impending titanic catastrophe? Or is there more to this looming cosmic scenario? Join us as we examine the scientific possibilities of a Pluto-Neptune collision. Pluto, a former planet that was reclassified as a dwarf planet, remains a subject of intrigue in the vast universe. According to recent theories by leading experts, Pluto's orbit is perilously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are raising alarms about a potential catastrophic disaster between these two celestial bodies, which could have profound implications for Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. Since its discovery in 1930, it has not yet completed one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is marked by its highly eccentric shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unique is its inclination, tilted at 17 degrees to the ecliptic plane. The way Pluto follows its path is far more unpredictable compared to other planets. This inclination and eccentricity add layers of complexity to its orbital structure. One of the most fascinating aspects of Pluto's orbit is its interaction with Neptune's. For about 20 years during each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This raises the obvious question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers struggled to understand its peculiar path. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stands out due to its steep inclination and irregular shape. The realization eventually emerged that Pluto's orbit does, in fact, cross Neptune's. However, the stability of Pluto's orbit, despite these complexities, is evidence of the intricacies of celestial mechanics. The three-body problem in space involves determining how three objects, such as Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's akin to predicting their movements based on their starting positions and the gravitational forces they exert on one another. In Pluto's case, this problem reveals how its orbit, Neptune's orbit, and the Sun's gravity work together in a complex way. Key terms like non-synchronous libration, orbital precession, and VZK wobbling are crucial to this puzzle, as explained by astrophysicists. Non-synchronous libration in relation to Pluto and Neptune means that when Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is vital in preventing their orbits from intersecting. Orbital precession, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is situated far above their orbital plane, adding another layer of protection from potential collisions. Another key factor in this scenario is VZK wobbling, named after three scientists, V, Z, and K, who studied the motion of celestial objects. This wobbling describes how Pluto, Neptune, and the Sun pull on each other with their gravity. This gravitational exchange affects Pluto's erratic movement near the Sun. Despite Pluto's orbit appearing chaotic, this wobbling maintains its stability over long periods. The VZK wobbling shows that even in the seemingly chaotic universe, patterns and rules bring a degree of order. These forces ensure that Pluto's orbit remains stable, preventing it from crashing into Neptune or veering off course. This three-body problem is essential to understanding how these orbits evolve under gravitational interactions. Studying this helps us learn more about Pluto, our solar system, and even distant galaxies and their stars. Numerical simulations in the late 1980s revealed that, despite its stabilizing properties, Pluto's orbit is highly sensitive. Small changes in initial conditions could lead to vast differences over centuries. However, these peculiarities of Pluto's orbit have been shown to maintain stability over incredibly long time scales. Recent automated calculations have provided insights into how the giant planets, such as Neptune, Jupiter, and Saturn, affect Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. But Neptune isn't acting alone. Jupiter's immense gravity also plays a significant role in stabilizing Pluto's orbit, and Saturn contributes as well. These findings suggest that Jupiter's gravitational pull is strong enough to ensure Pluto remains on a steady path for eons, possibly even indefinitely. It seems Neptune, Jupiter, and Saturn work together to ensure Pluto continues its safe journey through space without running into trouble. These dynamics are crucial for maintaining order in the solar system. Without these stabilizing forces, our solar system could be far more chaotic. Bodies like Pluto could collide with others or be ejected from their orbits, triggering a chain reaction with other celestial objects. For Pluto, especially with discussions about its potential collision with Neptune in the future, understanding its orbit is essential. This provides a clearer picture of the dynamic nature of the solar system. The case of Pluto demonstrates that even the most seemingly unstable orbits can achieve a state of harmony through the complex interplay of gravitational forces. The delicate balance between these forces ensures the stability of Pluto's orbit and its unique relationship with Neptune. While the idea of a collision between the two might sound alarming, the principles of orbital dynamics make such an event highly unlikely. The intricate dance of celestial bodies in our solar system serves as a testament to the power of gravity and orbital mechanics. Pluto's oddities, its elongated orbit, extreme inclination, and peculiar resonance with Neptune, highlight the beauty of cosmic order amidst apparent chaos. Despite its reclassification as a dwarf planet, Pluto remains a key player in scientific research, revealing critical insights about gravitational interactions and the forces that govern planetary stability. Its stable, albeit eccentric, orbit stands as a reminder of the intricate balance that keeps our solar system intact. The theories suggesting a potential collision with Neptune, while captivating, are speculative and highly improbable given the established mechanisms of orbital resonance, libration, and gravitational stability. Instead of impending doom, Pluto's relationship with Neptune showcases the elegance of the universe's natural laws. This celestial relationship also fuels the ongoing study of exoplanets and distant star systems. Understanding the delicate gravitational interactions within our solar system can provide clues about the formation and evolution of planetary systems elsewhere in the cosmos. For now, Pluto continues its slow, deliberate journey around the Sun, a silent witness to the grandeur and complexity of the universe. It reminds us that even the smallest and seemingly insignificant bodies can hold profound mysteries and lessons about the cosmos. As humanity advances in space exploration and our understanding of celestial mechanics deepens, Pluto will undoubtedly remain a subject of fascination, an enigmatic traveler in the vastness of space, forever linked to the intricate choreography of the solar system. Inside the not-so-distant future, the resonance between Pluto and Neptune ensures that their orbits never converge simultaneously. This powerful relationship is a consequence of millions of years of gravitational interactions that have sculpted the paths of celestial bodies in the solar system. It's a testament to the intricate dance of planetary mechanics, where chaos gives rise to order over vast timescales. Additionally, advanced simulations and mathematical modeling continue to refine our understanding of these interactions. Astrophysicists use supercomputers to simulate the movements of Pluto, Neptune, and other bodies in the solar system over billions of years. These studies reveal not only the stability of Pluto's orbit, but also the resilience of the solar system as a whole. Despite its reclassification as a dwarf planet, Pluto remains a source of fascination for scientists and the general public alike. Its icy surface, mysterious atmosphere, and unusual orbit offer clues about the formation and evolution of the solar system. As we continue to study Pluto and its interactions with other celestial bodies, we gain deeper insights into the forces that govern the universe. For now, the possibility of a collision between Pluto and Neptune remains a theoretical curiosity rather than an imminent threat. The gravitational safeguards in place, including resonance and orbital precession, ensure that these two celestial neighbors maintain their delicate balance. Pluto's story is a reminder of the beauty and complexity of the universe. Its eccentric orbit exemplifies how harmony can emerge from the interplay of gravitational forces. As we explore the mysteries of space, Pluto will undoubtedly continue to inspire wonder and curiosity for years to come. Orbital mechanics also highlight the importance of consistent observation and evaluation of these peculiarities to better understand our place in the cosmos. Examining the significance of space often leads us to confront the extraordinary nature of celestial bodies. For example, Pluto's orbit is a perfect illustration of this phenomenon. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is clearly demonstrated with Pluto. This means that even slight changes in the dwarf planet's position or velocity can significantly alter its long-term orbit. Using digital simulations has been incredibly valuable for researchers in deciphering how Pluto moves through space. These simulations utilize complex mathematics to model how Pluto and other space objects, like Neptune, interact gravitationally. By tweaking small details in the simulations, space scientists can understand how even minute changes can result in significant differences in Pluto's eventual position. In the late 1980s, these simulations revealed something intriguing about Pluto's orbit. Despite having stabilizing features like asynchronous libration and orbital precession, Pluto's orbit can still be inconsistent and unpredictable. Even a slight variation in Pluto's position or speed at the outset can lead to a completely different trajectory within just a few years. Yet, despite this chaos, Pluto's orbit remains stable over immense timescales, spanning billions of years. This demonstrates that Pluto's journey around the Sun follows a certain order, even though it may appear chaotic at first glance. Predicting celestial movements, especially when they involve irregular orbits like Pluto's, is a massive challenge. The inherent instability of such systems means that long-term predictions are often fraught with uncertainties. While mathematical models provide excellent tools for understanding and forecasting the movements of celestial bodies, they also highlight the limitations of our predictive capabilities. These models rely heavily on the precision of initial conditions, and even small errors or deviations can lead to vastly different outcomes, making accurate predictions a daunting task. Beyond the chaotic nature of planetary orbits, Pluto reminds us of the ever-changing and dynamic nature of the universe. While we have made significant progress in understanding space, Pluto's case serves as a reminder of how limited our knowledge of the universe remains. Grasping the gravitational effects of the giant planets on Pluto's orbit offers valuable insights into the broader dynamics of the solar system. It illustrates how the presence and position of each planet can significantly affect the stability and trajectory of other bodies within the system. So why are leading astrophysicists recently raising concerns about a potential collision between Pluto and Neptune? Despite the intricate forces working to prevent such an event, Neil deGrasse Tyson, a prominent astrophysicist and a significant figure in advancing cosmology, offers a unique perspective on the mysteries of our solar system, particularly the fascinating case of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, provides insightful analysis on the evolving nature of celestial mechanics and the public's interest in the less explored corners of space. Tyson's position on Pluto's reclassification is grounded in the ever-evolving understanding of our solar system. He views the reclassification not as a diminishment but as a meaningful adjustment to our growing knowledge of the diverse bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits like Pluto's as a reminder of how much there is still to discover in space. The fascination with these questions keeps the study of space so exciting. However, despite Tyson's optimism, his thoughts on Pluto's potential collision with Neptune paint a different picture. His concerns about the drift of Pluto's orbit suggest that we may still have many mysteries to uncover. Will Pluto collide with Neptune, Or is this simply another moment of confusion in the ever-changing universe of space? Only time and further research will tell. For now, we are left with a deeper curiosity about how little we still truly understand about our own solar system. We continue to study these celestial phenomena with the intent of uncovering more of the mysteries that lie beyond. The possibility of a Pluto-Neptune collision raises further questions about the intricate and captivating universe in which we exist. The potential for an encounter between Pluto and Neptune challenges our conventional understanding of planetary stability. That two celestial bodies with such vastly different characteristics could collide is both unsettling and fascinating, especially given the current relative stability of their orbits. Pluto, situated in the outer reaches of the solar system, far from the major planets, is a frozen world covered in nitrogen ice, with an atmosphere composed mainly of nitrogen, methane, and carbon monoxide. On the other hand, Neptune, a gas giant, consists mostly of hydrogen, helium, and lighter elements, with a thick, deep atmosphere. A collision between such disparate bodies would profoundly affect their structures and behaviors, potentially creating an event observable across vast cosmic distances. What makes this hypothetical collision particularly interesting is the influence of other planets and bodies in the solar system. While Neptune's gravity plays a dominant role in maintaining Pluto's orbital stability, it is not the only factor at play. Jupiter, the largest planet in the solar system, also exerts a stabilizing effect on Pluto's orbit, preventing it from straying too far into Neptune's domain. Furthermore, Saturn's gravitational influence adds another layer of complexity to the dynamics of the outer solar system, making a catastrophic event between Pluto and Neptune highly unlikely. Nevertheless, ongoing research has shown that the relationship between Pluto and Neptune is not as straightforward as a direct collision course. The gravitational resonance between the two planets, where Pluto completes 2 orbits around the Sun for every 3 of Neptune's, creates a kind of cosmic lock that prevents them from coming into direct contact. This resonance is a key reason why Pluto and Neptune's orbits, despite crossing in the vast expanse of space, have never resulted in a collision.